For energy and head of flow, usually kinetic energy and potential energy are the two commonly recognized forms of energy. But here in flowing fluid, we have the kinetic energy, potential energy, the pressure of the fluid, and other forms of energy that could be present in a flowing liquid. So usually we express the energy in terms of head. So the head is the amount of energy per Newton or per pound of a fluid. So the first type of energy present in flowing liquid is the kinetic energy. So the kinetic energy is the ability of a mass to do work by virtue of its velocity. So here is our equivalent formula for the kinetic energy. WV squared over 2G. But if we are going to express that into its velocity head, uh, since the head is defined as the energy per unit per weight, we cancel out the W. Okay, so let's say we have here point 1. This is a pipe. We have a flow of the pipe going from point 1 to point 2. So if we have a value of the mean velocity at point 1, we will be able to determine the velocity head by using this solution. V1 squared over 2g. We can also determine the velocity head at point 2 if we have a value for the velocity at point 2. Okay, next, the elevation energy or the potential energy. In connection to the action of gravity, elevation energy is manifested in a fluid by virtue of its position or elevation with respect to a horizontal datum plane. So if we have a reference point or datum where we have the value, let's say that datum has an elevation of 0. Okay, so if we are going to determine the potential energy at point 1 or point 2, so we can use this equation. This is an equation from physics for the potential energy, or we have there mgh, or weight multiplied by the z distance, or the distance or the position or the elevation of that point from the datum. So we have mgz. So that z is measured from the datum going to the point where we are going to calculate the potential energy. So this is distance z. This is also distance z. Okay, z at point 1, z at point 2. So for the potential energy, for the equivalent elevation head, pressure head for that, for the potential energy, we only have Z when we cancel out W. Okay, so again, the head, elevation head or the pressure head for that particular energy is just equivalent to the energy per Newton or energy per weight. So we only have Z for the elevation energy. Next, we have the pressure energy. So a mass of fluid acquires pressure energy when it is contact with other masses having some form of energy. Pressure energy therefore is an energy transmitted to the fluid by another mass that possesses some energy. So pressure energy is also under the potential energy, and we have an equation for the pressure energy of W multiplied by the pressure divided by the unit weight. Okay, so the pressure head, if we will divide it by the weight, we will have the pressure to be divided by the unit weight of the fluid. Okay, so combining all the energies present on a section of a pipe, the total energy or head in a fluid is just the sum of the kinetic and potential energy. So again, potential energies are pressure energy and elevation energy. So combining the two, the kinetic and potential energy, we have the sum of kinetic energy plus pressure energy and the elevation energy. So if you're going to compute the total head, just add the velocity head, the pressure head, and the equivalent. So usually if we are required to determine the total energy, it is referring to the total head. That's why we have an equation here for the total energy, which is v squared over 2g, the velocity head, p over gamma, the pressure head, and z as the elevation head. So our total energy here is expressed in meters. Okay. For the power and efficiency, power is the rate of doing work per unit of time. For a fluid of unit weight, gamma in newtons per cubic meter, and a flow rate of Q in cubic meters per second, with a total energy computed E in meters, which is the total head, the power watt is Q gamma E. So, substituting the values for Q, gamma, and E with these units, Newton per cubic meter for gamma for unit weight, cubic meter per second for flow rate, and meter for the total energy, we can compute the power. So that unit will be in watt. Okay? So, the efficiency usually more likely this is applicable when there are turbines or pumps that is installed in the pipe, so that we can determine how efficient it is. So to compute the efficiency, we have here output divided by the input multiplied by 100%. So what do you mean here by the output and input? Let's say this is our pipe where we installed turbine or pump. Okay, let's say pump because it's going upward. So if we computed the power at point 1, okay, that will be your input. Okay, power input. And when we computed the power at point 2, okay, that will be our power at the output. So we will be able to compute how efficient, usually we compute the efficiency of the pump, or if it is going down, the flow is going down, we use turbine. Okay, so we can compute the efficiency of that installed pump or turbine when we compute the power on the input and power at the output. Okay, so here are the conversion factors for power, from horsepower to watts, horsepower to foot-pound per second, and watt to joule per second. Okay, next. So knowing the energies present in a fluid flowing in a pipe, so we can now apply Bernoullis Energy theorem. So applying the law of conservation of energy, considering that that fluid is incompressible, Bernoullis theorem states that neglecting head loss, the total amount of energy per unit weight is constant at any point in the path of flow. Let's say in this figure we have pipe where a liquid flowing from point 1 going to point 2. So according to Bernoullis energy equation, we will neglect the head losses. So usually these head losses are the friction in the pipe, that may cause to the reduction of energy from point 1 to point 2. So the total energy at point 1 is equal to the total energy at point 2. So no head loss is the ideal condition leading to the theoretical values in the results. Again, recalling the energy is present at point 1 and point 2. We have the elevation energy. So if we have here the datum, if we are going to determine the equivalent elevation head, this is distance z. Okay, and if we have here the pressure head, so the pressure head will be this one, P1 over gamma. So the pressure head, so that total distance from the pipe to that point, okay, is our reference point for our hydraulic grade line. So another, we have the velocity head or the velocity energy. So we have V squared over 2G. So that point from the hydraulic grade line up to that point is your energy grade line, reference point for energy grade line. On the other hand, we have at point 2, we determine the elevation head Z, that is Z2, the pressure head. So that computed pressure head and the velocity head. So theoretically, according to Bernoullis Energy Equation, is that the sum of this velocity head, pressure head, and elevation head on point 1 and point 2 are equal. That's why when we try to draw it here, those elevations, those pressure heads and velocity heads, we will have the same height, total height of those energy head. Okay, so if we are going to make an equation using the Bernoullis energy theorem, we have E1 equals to E2. So again, if we include W for pressure, velocity, and elevation energy, this will just be cancelled out because all the terms have W, have weight. So therefore, our Bernoullis equation is this one. Okay, the sum of the velocity head, pressure head, and elevation head for point 1 is just equals to the sum of those heads of energy heads at point 2. Okay, so since here in Bernoulli equation the head loss is neglected, but if we want to consider the head loss in the pipe, so usually we have frictional head loss, internal head loss due to internal friction, and there are other factors that may cause the reduction of energy from point 1 going to point 2. So speaking of head loss class, this will be discussed on the later part of our lecture in hydraulics. But if we are going to consider the head loss, so the energy equation for that is that we will just subtract the head loss on the energy one where the flow comes from, or the starting point of the section where we were going to determine the energy, and we will subtract the head loss at point 1, and that will be equivalent to the energy at the end point or point 2. So almost similar sa Bernoullis equation, we will just take the sum of the pressure head, velocity head, and elevation head, and okay, so here in Bernoulli equation, we neglect the head loss, but in reality class, there are losses in energy as the fluid flows within the pipe. So from point 1 going to point 2, we expect that there will be reduction of energy going to point 2. So most of the time we have there the head loss due to the internal friction of the pipe. So we should really consider this head loss. So how do we apply head loss, or how do we include the head loss in our computation? So in making the energy equation, considering the head loss, applying again the principles of conservation of mass, is that the energy at point 1 should be equals to point 2. Only that we have to consider the head loss. So if we are going to consider the head loss, so it means that we will subtract the head loss at energy at point 1, and that will be equivalent to energy at point 2. So the diagram for our hydraulic grade line and energy grade line looks like this. Okay, so there will be reduction in the value, or the total energy of the velocity head, pressure head, and the elevation head. So that difference from energy at point 1 to energy at point 2 will be your head loss. Okay, next, when we use pumps, so usually we use pump to raise water from lower elevation going to a higher elevation. So the use of pump is basically to increase the energy of flow. So the pump consumes electrical energy, which is our input, okay, and delivers flow energy, which is the output. Okay, so again, the pump will increase the energy at point 1 in order for us to have the same energy as 2.2. Applying again the energy equation, considering the head loss. So if we have head loss here, we will subtract again the head loss and the energy at point 1 from the starting point, and also we have an additional head due to the pump. Okay, so the head is an additional, the pump gives us an additional head at point 1. So our symbol for that head is HA. So it will be added at the energy at point 1, and that should be equals to 0.2. So by the way, class, speaking of head loss, this will be discussed later on our lectures in hydraulics, but not in this lecture video. So this will be on the later part of our lectures in hydraulics. So again, applying again the, or taking again the sum of the velocity head, pressure head, and the elevation head, and including the head due of the pump and the head loss, this is plus, and this will be our equation. Okay, considering the head due to the pump. Okay, so to compute the output power of the pump, so the additional head that we have will be multiplied to the flow rate. Okay, the flow rate at point 2, where but of course the flow rate at point 1 is just the same at point 2. So the flow rate on the pipe, and the unit weight of the fluid, and H of A. So for the turbine, okay, so again, the pump, the purpose of the pump is to increase the energy from point 1 going to point 2. On the other hand, the purpose of turbines, when we use turbines, is that we will extract flow energy from from the fluid that is flowing in the pipe and convert it into mechanical energy, which in turn converted into electrical energy. So the purpose of turbine is for us to generate electricity. So usually turbines can be found on dams or hydroelectric power plants. So as liquid flows from point 1, that energy from point 1 will be deducted or reduced by the energy due to the installed turbine. So it means that the energy at point 1 will be subtracted by the equivalent head on the turbine. So our symbol for that is HE for the head of the turbine, and that will be equivalent to our energy at point 2. So it means, applying again the energy equation, uh, we have the energy equation which is equals to energy at point 1 minus the head of the turbine. So unlike in the pumps, we increase the energy, but here the energy is decreased. Minus head loss again, if we want to consider the head loss, and that will be equals to energy at point 2. So again, same solution for the energies, only that we have negative head for the turbine. So for the output power of the turbine, same solution as with the pump. So multiply the flow rate to the unit weight of the fluid and the head of the turbine. Okay. So let's now apply Bernoullis equation as well as the energy equations that we have discussed here. So let's answer some sample problems.